Anirban. So thank you very much. And it is my pleasure to be the chairperson for these three talks right now. And we will start with Surya Ramana, who will speak of a problem of Sharkozy. So please, Surya.
Okay. Thank you so much, Michael. Thank you very much to my dear friends who have organized this program. Adhikari Dada, Anirban, Sauli, Purushottam, Anup, and others. And of course, great thanks to Balu for causing this opportunity and for everything, to use Professor Desir's phrase, I've known him also for 70 by 2 years, and it's been a really, really long time. So thank you very much to all. I should like to just add a small caution here. The internet in HRI can be quite unstable nowadays for some technical reasons. So I might just have to stop my talk mid-sentence. Please don't be alarmed if that happens. I do hope nothing will happen. Okay, so let me get to the subject of the talk, which is on a problem of Sharkozy. So this is a problem that I have lectured on many times. Each time we have managed to add some small development to the work we had done so far. So let me just begin by introducing the question, which is like this. So what is the problem that Sharkozy proposed? Sharkozy, in the year 2000, András Sharkozy, I think it was just 1 year before 2000, the paper was published in Acta Math Hungarica in 2000. It was a long list of problems that he was posing for younger mathematicians, I think on the occasion of his 60th birthday or so, I'm not very sure. But it's a list of problems, a lot of interesting problems. So one of the problems in this list is this question, which I state in parts here. The question combines the two classical themes, the Ramsey theoretic problems and Waring's problem. So the question is like this. Given the S is the set of squares and K is an integer greater than or equal to 1. Then you are supposed to find an integer which is now written as little sk. Now, what is this little sk? The definition of little sk is this. For all large integers and any partition of the squares, so over all possible partitions of the squares into K disjoint subsets, okay, into K disjoint subsets. So for all large enough integers and all partitions, so for each large enough integer given partition, there should exist J such that n can be written as x1, x2, so on up to xm, with each of these summands belonging to the same Sj, okay, and the number of summands does not exceed Sk. So you have to find the smallest integer Sk, which has the property that given any K coloring of the squares, all sufficiently large integers have a monochromatic representation. That means can be written as a sum of squares, all summands belonging to the same set of the partition, and the number of summands not exceeding Sk. Of course, the color, namely the summand that is the subset of the partition that is used, can vary with n, but each n should have a monochromatic representation as a sum of squares. So, and the question of Sharkozy was to find the smallest integer Sk such that this sort of expression is possible. So this is uniform over all partitions. Of course, as soon as such a definition is given, it's natural to ask, does such an Sk exist at all? Is there such a smallest integer or is it infinite? We will see in the course of the talk that it is not difficult to show actually that such an Sk exists. the question is of sharp bounds for Sk. So let me just move on. So we will restrict ourselves to optimal upper bounds. We will restrict ourselves to optimal upper bounds for Sk, Tk, and Rk for large primes. So let me just say what are Sk, Tk, and Rk. So here are variants of this question that you can immediately pose. For the set of squares, the number is called Sk. So Sk is the smallest number such that in any monochromatic, any K coloring of the squares, every sufficiently large integer is expressible as a monochromatic sum of at most Sk squares. Now, for the set of primes, one can pose a similar question. So Tk is the smallest integer such that for any K coloring of the primes, every sufficiently large integer can be written as a sum of at most Tk monochromatic primes. And similarly, Qk and Rk, you can pose the same question for any higher power rather than simply the squares. Okay, I couldn't resist the temptation of using this notation because I am a bit of a fan of ancient Rome. So you have SPQR for these various sets here. Okay, so now with these notations, so these are the various sort of problems that one can pose. And as you can see, you can basically pose this question for any set instead of the squares, which is an asymptotic basis for the natural numbers. So all large enough natural numbers can be written as sums of elements of that set. Then you can partition that set into K subsets and ask for the smallest integer such that every sufficiently large integer is expressible as a sum of monochromatic terms from this set. So this is a general question that one can pose. Sharkozy posed it for the squares and for the primes, but we will also consider the prime squares, which at least to us personally, Enkar asked us. It's a natural question, and it was independently considered by Guahua Chen. Okay, so these are the sort of questions that we have. Now, let me speak of the most obvious coloring that one can consider. So you can partition the squares or any set. The most natural way of partitioning it would be to use residue classes modulo a suitable integer m. So you fix an integer m, and then you use the residue classes to partition the given set. So let's just look at an example for the primes P. So you take m any integer and fix k to be 1 plus the number of invertible classes modulo m. So one more than the number of invertible classes modulo m. So then let a1, a2, ak minus 1 denote the invertible classes modulo m. So now you can partition the primes in the following manner. So you put all the primes which lie in a particular residue, invertible residue class modulo m in one of the sets. So you have k minus 1 such subsets of the primes, sorry, excuse me, k minus 1 such subsets. So k minus 1 such subsets of the primes, and the last one you take the primes that divide the modulus itself. So we have k subsets of the primes, and this is a disjoint partition of the primes. So this is a coloring of the primes. So now let us try to see how many summands are required if I want to express a number which is a square, which is a number greater than m square and is divisible by m. Let us try to see how many summands we require in order to express such an n as a monochromatic sum using this partition. So suppose that n can be written as x1, x2, xt with all xi's of the same color. What this means is that the xi's all belong to a particular one particular element of this partition. Okay, so suppose n has such a representation. I claim that T, the number of summands, is at least m. So the reason for this is quite simple. So let us see the reason. Suppose n can be written as x1, x2, so on up to xt as a sum like this. And all the xi's belong, let us say, to the invertible class A mod n. Okay. This means that n is equal to A times, because all the xi's are A mod m, this means that n is A times T mod m. But m divides n and A is co-prime to n, which means therefore that m must divide T. And therefore T must be at least m. Otherwise, if n is, if the xi's all don't belong to the same residue class mod m, then the color that is being used is the last one, which consists of prime divisors of n. So that means all the xi's are actually divisors of n. But n is larger than m square, and each of these summands can be at most m, and therefore the number of summands should again be at least capital M. So either way, arguing, I mean, no matter how you represent n as a monochromatic sum, you're forced to have at least m summands. Okay, so this is one particular coloring of the primes, but naturally, if you're looking at tk, which is defined uniformly over all colorings, this lower bound here will automatically give a lower bound for tk itself. So tk, the number we are seeking for the primes, is at least m. And since, of course, writing m as k times m by 1 plus phi m, because 1 plus phi m is the definition of k, so you write it like this, and then you choose a suitable m, then you can you choose a suitable square free m dependent on k, then you can see that tk is at least k log k. Okay, you can make a more refined calculation, and indeed this is what Egivari and Enkar did in the first paper written on the subject of Sharkozy's problem, and they proved that tk is at least e to the gamma, the usual numbers that appear in prime number theory, e to the gamma times k log k. Okay, so this is the lower bound for tk. It's an obvious lower bound that comes out of simply partitioning the primes using an appropriate modulus. You can similarly get lower bounds for this for the numbers, analogous numbers. So let us just have these lower bounds. Oops, yeah. So all these lower bounds are of order k. That's firstly the important thing to notice. So for the primes, tk is bigger than e to the gamma times k times fudge factor, which is log k. For the squares, it's k times another factor, which is exponential log 2, log k by log k. For the prime squares, it's the same sort of the bound for squares gives one for prime squares, because whenever you color all the squares, you end up inducing a coloring on the squares of prime numbers. So you get therefore these lower bounds. Notice that this log k comes from the factor m by phi m, which is basically the reciprocal of the density of invertible classes mod m. And similarly, these factors, the exponential factors here, arise from the density of squares, invertible squares modulo m. So the reciprocal of these densities gives you these extra factors. So what you want to remember is that the lower bounds are all of order k times fudge factor, which comes from appropriate density. So now what are the upper bounds? So Egivari and Enkar, in the same paper that I spoke of, they showed that tk is less than 1500 k cube. So you see that upper bound was of the order of the cube of k, whereas the lower bounds are of the order of k. And similarly for the squares, they had a bound which is even bigger, it's k log k to the 5. So then Olivier and myself, we worked on this question, and we could obtain an upper bound which was the same order as the lower bound. In principle, you can even write down a constant here. So up to this constant, we essentially got the optimal answer. So Tk is k log log. Then subsequently in 2015, Akhilesh, who was then a student of mine, we worked for squares and we got the bound. So we reduced the k log k to the power of 5 to k squared to k to the power of 2 plus epsilon. Then in 2018, Olivier, Gyan, and myself, we could get for the squares a bound of order k, but please notice, and this is still an annoying thing that we have not been able to settle, our exponential factor has a 3 log 2 rather than the log 2 in the lower bound that is there. So we are off by a power of 3 here. Otherwise, you have the same factor log k by log log k. So you have log 2 here, whereas our upper bound is a 3 log 2. I will explain at the end of the talk why we get a 3 log 2. And essentially, the obstruction is counting points, getting the correct count for points on a certain variety over a finite field. It just turns out that we are not able to do what should be the correct answer. If we are able to, we would be able to replace at least this 3 by 2 without any other change in our method. And perhaps if the method was refined, you could get the same bound here, but I'm not so sure if 2 log 2 is the correct answer or log at this stage. So that's the result for the squares. Now, recently, for the prime squares, Chen had obtained in 2016 the upper bound like we had obtained for the squares with Akhilesh. Rk is less than k to the 2 plus epsilon. And Gyan, myself, and Malaysian, who was a student at HRI earlier, we could get an analogous bound as we got for the squares with Olivier for the prime squares. This we got some time back, it's been in preprint form. Only recently could we put it in final form, and therefore this is the last result we have, which is about, published last year. So this is the story so far about the upper bounds and lower bounds. As we said, for the primes, we have basically solved it some years ago with Olivier. And for the squares, we have gotten close, but still there is this extra annoying factor of 2. So let us now look at how one obtains these bounds. So here is a toy bound that I sketched to give you the method, to give you an idea of the method. So let me sketch a proof for Tk being less than k to the power of 4. So what I want to prove is that if you give me, if you color the set of prime numbers in k different colors, then every large enough number can be written as a sum of at most k to the power of 4 primes, all having the same color. So I'm going to sketch a proof of this fact for you just now. So let us suppose that this is a coloring of the primes in k colors. So P is written as a union of k subsets which are disjoint. Now let's take a large integer n, so n to 2n, and consider the intersections of these PIs with this interval and call them the Roman PIs instead of the script PIs. So you have PI is equal to this, and P is the full set of primes in the interval n to 2n. Okay, then P naturally is the union of all these capital PIs. And simply by the pigeonhole principle, at least one color, there's at least one index I, which has more than 1 by k, more than or equal to 1 by k of the total primes in the interval n to 2n, simply because there are k of them. Okay, so let us denote this particular index. There may be more than one by S. So just choose one which has more than 1 by k of the primes in the interval, and let us call it S. And let us denote by ES the additive energy of S. Now, the additive energy of S is a fundamental notion in additive combinatorics. It's one of the most basic tools in additive problems. You use this additive energy to get lower bounds on representation of integers as sums of particular as sums of elements of particular sets. So ES is the number. The definition of ES, the additive energy of a set S, is the number of solutions to this equation. So it basically counts the repetitions in additive representation. So x1 plus x2 equal x3 plus x4 with all the xi's belonging to S. A count for this, the number of solutions to this equation is called the additive energy. Now, since S is this subset Pi, and Pi is a subset of the full set of primes, plainly from the definition, it follows that the additive energy of Pi is less than the additive energy of the full set of primes in the interval n to 2n. So the arbitrariness in the choice of Pi is gone when you use this inequality. So now I just need an upper bound for the number of solutions to this equation, with the xi's being any prime number in the interval n to 2n. That's a very classical equation that's been studied from the time of Schneiderman's density theorem and so on. It's absolutely well known, and you can very easily, using standard tools nowadays, any basic C or circle method, whatever you like, you can immediately write down an upper bound, which is of the form, which is the expected form, namely n cubed by log n to the power of 4. Because there are n by log n choices for the first three variables, and the fourth one has a chance of being a prime, which is given by 1 by log. So this is the expected upper bound, and you get that very easily using any basic tool in analytic number theory. Now the point is, since we have this bound for S, and S is large in cardinality, it has 1 by k of the total set of primes in the interval. You see that cardinality of S is greater than n by k log n, and what you get from here, you can rewrite this particular bound for ES in this form. ES is less than S cubed k cubed by log n. Now there is a absolutely classical Cauchy-Schwarz application, which is again fundamental to additive number theory, which relates the cardinality of the set S plus S, namely the set of integers which are sums of two elements of S, to the additive energy and the cardinality of S itself. So this inequality explains why additive energy upper bounds are so important for lower bounds for representations. Okay, so this is a very standard classical Cauchy-Schwarz application, and it gives you this. So if you plug in the bound that I wrote down above into this Cauchy-Schwarz application, and recall that S has at least 1 by k of the total number of primes, then here there's evidently, okay, so then you cancel the S cubed and you get a cardinality of S. You put an n by k log n, k cubed. The log n's cancel off, and you conclude that S plus S has the cardinality of S plus S is 2n by L plus 1, is at least 2n by L plus 1, where L is some constant times k to the 4. So what this means, and this is very simple, but the remarkable fact, is that you started with a set of prime numbers S, which is large in the set of prime numbers between n and 2n. But as everybody knows, the set of primes itself is a very sparse set of the total integers in n and total integers in the interval n to 2n. Nevertheless, we concluded using additive energy and so on that the sum set of this set of primes has actually positive density in the interval 2n to 4n. It has more than 2n by L plus 1 elements, where L is C k to the 4. So we, starting from a set of primes, we have just added it to itself and arrived at a set which has positive density in the full set of integers. So this is a classical move again in additive number theory, and explains, this is the basis of various methods for old methods for trying to attack Goldbach problem and things like that. So we have this particular thing. Now, what's the use of this in our context? Now, we know that S has positive density in the interval 2n to 4n. Okay, so this if you call A as S plus S, then S plus S has positive density. So this is the set A, and A has more than this many elements. One would expect that if I went on adding A to itself, I'll eventually get an interval, because A has positive density in an interval. So if you added it to itself sufficiently many times, you should probably generate a whole interval. Of course, that is not true. For example, A can consist of even numbers, and so no matter how many times you add, you're going to only get even numbers and never a full interval. But then that tells you that the right thing to expect is that if you add A to itself, you should at least get a long arithmetic progression. This is true, and this is the basis of several theorems called addition theorems in additive number theory. And one such theorem, which is relatively late, is Sharkozy's, so a theorem of Sharkozy himself, called Sharkozy's finite addition theorem. So what does Sharkozy's finite addition theorem say? It tells you that if A is a subset of 1 to n, and A has a positive density in this interval, this has nothing to do with prime numbers. Just take any subset which has positive density in the interval, and then there are numbers D and H which depend only on this density. So there is some explicit upper bounds here. D is less than K, H is less than 118 times K, and such that if you add A to itself H times, it would contain an n-term arithmetic progression. You see, n is this number n here. So it would contain an n-term arithmetic progression to modulus D. Okay, n-term arithmetic progression of this type. The only thing you don't control is where the arithmetic progression starts. But you have an n-term arithmetic progression of this type. So it has, it's just multiples of D. If you start with A in an initial interval, if you translate, if you take A in an interval like n to 2n, as we are doing, you will actually get an arithmetic progression with the first term, and not just multiples of D. Okay, so what Sharkozy's theorem tells you, and the remarkable thing is that the modulus of the arithmetic progression is bounded by the density explicitly. There's a clear bound. You don't lose anything. The density bounds this. And also, it tells you that the number of summands that you need, so the number of times you need to add A to itself to achieve this, is bounded again explicitly in terms of the density. Okay, so this is Sharkozy's finite addition theorem. Of course, this theorem itself is a culmination of a number of results in the literature, and this was itself refined by Lev. So we nowadays have the sharpest form of this theorem, which I will get to in a little while. So therefore, oops, I don't know what's happening now. Sorry, the screen has changed a bit. Are you able to see the screen properly, or?
Can you reduce it a little bit as it was before?
I don't know how to reduce this thing. Gosh.
Come out of full screen. Maybe just double click.
Okay. I will have to stop this share and start again.
But it's almost completely visible to me. So just a little bit on the margin on the right is not there.
Let me just see. Oops.
Yeah.
Oops.
So during this break, if some of you has some question, it's time to ask. Any question? You can use the chat also to ask your question. I will give them to Surya.
Can you now see it?
No.
Not yet. No.
No? Okay.
No.
Just one
Share
moment.
the screen.
Yeah, I have to share the screen. Yeah. I've shared the screen. Excuse me. Is it okay?
Not yet. No, we do not see your screen. Okay.
Now?
No, it's okay.
Okay.
Good.
Great. Sorry for the interruption. Yeah. Right. So where were we? This next. Yeah. So this is where I was. That Sharkozy's finite addition theorem tells you that if you take a subset of 1 to n, which is itself dense, and you know the density, so this k here representing the density, then you know that if you add a to itself sufficiently many times, and that number of times is controlled by the density, then you have an arithmetic progression of length n, whose modulus is also controlled by the density. Okay, so this is the key thing. Now, in this situation, if you now apply it to what we have, so you take S, which is a subset of the primes. So this primes denoted with blue. So S has 1 by k of the primes in it. Then we have seen that S plus S has positive density. And if you add S plus S to itself h times, so that's equivalent to adding S to itself 2h times, then 2hs will contain a long arithmetic progression, an arithmetic progression of n terms with a modulus d, which is controlled entirely by the density. Now, this is very nice. So you have shown that there are n elements. So the n terms of this AP can all be written as exactly as sum of 2h elements of S. Exactly 2h, not at most 2h. So this AP lies inside this set 2hs. Okay, so the AP has, each term in this AP can be written as a sum of 2h elements of S, and h is controlled by the density, which is very good, but we don't want an AP, we want an interval. So here is a small but very crucial, very nice and crucial observation of Enkar and Egivari, which is simply that S, of course, we are dealing with a set of primes. So it contains a number which is co-prime to every number less than the bound for the density. You see, there is a bound for the density. And since S is in n to 2n, and n is at your choice, it's a large integer, and the modulus of this arithmetic progression is bounded just by the density, you can just choose practically any element of S would be co-prime to all integers up to the density, up to the modulus of the arithmetic progression. So the net result is your arithmetic progression has a modulus which is co-prime to an element of S. And the number of terms in this arithmetic progression is larger than this element of S, because the elements of S lie between n and 2n, whereas your arithmetic progression is between 2n and 4n. Therefore, you have an AP with a modulus that is co-prime to a number and number of terms larger than that number. And so the arithmetic progression represents all distinct classes modulo that number x. Therefore, every integer can actually be written as an element of that arithmetic progression times a multiple of x. And this holds for every integer, except that, of course, these number r need not be positive if n is not sufficiently large. So what we have seen using Sharkozy's finite addition theorem is that every integer can be written as an element of this arithmetic progression plus a multiple of x, and x is an element of S. Now, the arithmetic progression, each term of this arithmetic progression A is itself a sum, can be written as a sum of 2h elements of S, and H is controlled by the density. So if I can bound the number of R, the number R appearing here again in terms of density, then I am done. Then I would have shown that for large enough integers can be written as sums of elements of S, and I know that I have explicit bounds on the number of summa. Now this can't be done for every integer, but for integers in a certain interval, it can be done. And using this, one can conclude, for example, so this is the sort of conclusion we have. You start with a set of primes. So you start with the full primes, you divide the primes into k subsets, you choose one which has at least 1 by k of the total primes, you apply this additive energy bound and everything, and finally you conclude that using Sharkozy's finite addition theorem, that every integer in this interval, this 236 ln to 237 ln, where L is this number which is entirely given by the density 180 times some absolute constant times k power 4. Every integer in this interval can be written as x1 plus x2 plus xm with all the xi's lying in S. So you see that you have represented every integer in this interval as a monochromatic sum, as a sum of elements from a particular subset of the partition, a subset which has at least 1 by k of the total primes. Now the point is that these intervals, so with each n you have associated an interval where you can represent all integers as required. And the point is that these intervals themselves, as you vary n, they intersect. And so you cover a neighborhood of infinity. So you change n to n plus 1, and this interval that you get changes to another interval, the one corresponding to n plus 1, but all these intervals intersect, and therefore you successfully represent all sufficiently large integers as monochromatic sums of primes. So that's what is written here. In is the intersection of in and in plus 1 is not empty, and therefore you have succeeded in representing all large enough integers as monochromatic sums of primes. So what does this finally mean? You can write this down as a strategy. So you can write the principle as a lemma. Okay, so this finally we kind of ironed it out a bit and put it in this paper with Gyan and Olivier. And lemma is this. So suppose you have any subset, nothing to do with the primes, just any subset of an interval which is written as n to n plus L. Okay, and define EMS as the number of solutions to this equation, where m is at your choice. So this is the m-fold additive energy. Suppose you can get a bound for the m-fold additive energy, which is s to the cardinality of s to the 2m times some d by L. Now, cardinality s to the 2m by L is basically what is the expected bound for the number of solutions. Okay, because the chance that you see each of these variables belongs to S, that gives you S choices for all variables except the last one. And the chance that the last one belongs to S is, naively speaking, the cardinality of S by the length of the interval, which is S by L. So the expected upper bound for EMS would be cardinality S to the 2m by L. So this D represents some sort of a distortion from the naively expected upper bound. So if you can prove such an upper bound where D is some number, L is the length of this interval, and cardinality S to the 2m, okay, and L is larger than n, greater than this distortion as well, essentially. And if this set S contains a number which is co-prime to all small primes, so all primes essentially not exceeding this D, then every sufficiently large number can be written as a sum of elements of S. So what I'm telling you is that is a condition based on an upper bound for the additive energy, m-fold additive energy. So if you get an appropriate shaped upper bound for the m-fold additive energy, you can just plug this lemma in and conclude that every large enough integer can be written as a sum of elements of this set S. Now it's a question of bounding the number of summands, which you can easily control by limiting the size of this integer. And so for each interval n of the form n to 2n, you choose a particular S from your partition. You apply this, you get a interval where every integer can be written as a sum of elements from this S. Then you keep varying the n. The choice of color, the S would vary with the n. Nevertheless, the intervals in which you can represent all integers as monochromatic sums, those intervals will intersect, and therefore the union will give you all sufficiently large integers, and you have solved the problem of Sharkozy for a particular set for which you can get the appropriate bound. So the question then becomes, oops, excuse me, a lot. Sorry, this seems to be more serious problem. Yes. Therefore, this is the lemma that I spoke of. And now, in the remaining, how many minutes do I have?
10, well,
10.
well
10.
8.
Pardon?
8 minutes. 8.
8. Okay, I'll just try to finish in 8 minutes. So you see, therefore, this is the strategy for obtaining the results that I have mentioned. Now the question is, how do I bound this additive energy? Okay, so this is the result that we had with Olivier. So if you take a set of primes which is large enough in between n and 2n, then its additive energy is bounded by s cube log k by log n. This is basically the best possible bound that one can get. So the problem was reduced to bounding the additive energy, and this is the bound that we had. Now, when we obtained this result, Matomaki also obtained another result which is closely related with this. So I just would like to mention it for a moment. So if you take two subsets of the primes which have relative density alpha and beta, then she said that the relative density of the sum set has this. The relative density of some set is at least this much. Okay, this result is optimal, and Matomaki uses the method of Green and Tau to arrive at this result. Now, the method that Ramare and myself used, which is based on Ramare and Rusha, gives the same result on this problem, but with a factor of half. So it's lower than this by a factor of half. Essentially because the additive energy in our bound had a factor of 2. So this recently, a couple of years ago, we have refined, though we are still working on a sharper version of this result. So by refining the method of Olivier and Python, we have been able to recover the result of Matomaki, but in a slightly sharper form. Namely, we get a bound for the additive energy, from which again one can get this result back. Okay, this method uses the one of Ramare and Rusha, Ramare and myself, whereas this depends on the method of Green and Tau. So just to point that out. Now let's, to end the talk, let me simply tell you how, very quickly, how the additive energy is bounded. So additive energy, as I said, is just account for the number of solutions to this equation. Now, with the von Mangold function lambda, you can easily write the additive energy as satisfying this inequality. So the number of solutions to this equation times log n, which is the weight for each of these solutions being primes in n to 2n, must be less than or equal to lambda n times of lambda evaluated at x1 plus x2 minus x3. Basically, what we are doing is testing for when x1 plus x2 minus x3 is a prime. In order to count the number of solutions to this, I weaken it to simply asking, okay, tell me how many, for how many triples is x1 plus x2 minus x3 a prime between n and 2n. Okay, so one has this as the starting point. Then you use standard methods in analytic numbers. So you have a sieve identity, which is well known, and a basic sieve identity which you put in. Eventually use additive characters to represent the resulting summations, and then resulting congruence conditions that come out. And so when you do all of this, these are very standard steps in treating the problem. So skipping a number of standard steps, you arrive at the fact that your additive energy times logarithm of n is bounded by a sum of this type. So here q is an integer parameter that goes up to logarithm of n power 4. You have mu q, and then you have essentially the cube of the Fourier transform of the set S that you started with, which is just sigma ent n in S. Okay, so these are sums that are very integral to analytic number theory. The large sieve concerns itself a lot with these sums and so on. So we would like bounds when q is very small in relation to n. Okay. For all other sizes of q, we use standard methods and arrive at acceptable error, and so they are treated. Now, to treat this sum, one splits it as q dividing an appropriately chosen square-free integer and others. The other integers, because there's a mu q, the other integers are necessarily big, and so you arrive at two things. One is to estimate this sum, where q is large but less than log n to the power of 4, and you have a sum of this sort that you have to estimate. Now, this is a sum that Olivier had treated before, and this is treated by what he is called the improved large sieve for the primes. So this is a very, the large sieve itself, of course, is a very standard inequality in analytic number theory, and one of Ramirez's results was an improvement of this for the primes. Now, this large sieve is this inequality of Olivier's is extremely closely related to the restriction theorem that became famous later on in the work of Tao and Green. So it's basically that Olivier's large sieve treats Ferry series, whereas what is Tao's large sieve for the primes, which essentially gives the restriction theorem for the primes quite immediately, it treats a general well-spaced sequence. So those who are familiar with the theory of the large sieve will recognize that this is a special case. So, but of course, this is much before. So in any case, using Olivier's large sieve, so using Olivier's large sieve, we treat the case where q is, this parameter q is large, and then we are reduced to treating the case when the parameter q divides a particular fixed square-free number. This problem reduces actually to a completely combinatorial problem modulo this square-free number. And you can state that problem without reference to number theory itself. Because that square-free number, so when you look at the problem mod the square-free number by Chinese remainder theorem, it is split into product mod each prime dividing this number. And finally, the problem that you actually have can be stated in purely combinatorial terms. So the question is like this. Suppose I have a finite product of finite sets. Okay, just a finite product of finite sets. And I take any subset of the index set and I take two subsets in this product. The question is, estimate the number of pairs belonging to one of the sets, the second to the other, which differ in prescribed coordinates. So how many pairs A, B are there such that the ith coordinate of A differs from the ith coordinate of B, where I belongs to a prescribed set of indices. The question is, can you bound this number? So this, when bounded, gives the solution to the, so allows you that bound. If you substitute into this, you finish the problem. Okay, so you have essentially this bound, and with this you're done. Now the thing is, we originally with Olivier we got an extra factor 2, which we have removed with Malaysian and Gyarprakash, so as to be able to recover Mathemati's result. But we are still in the process of refining the error terms in this thing, so that should be done shortly. Anyway, let me just summarize the whole thing by saying that we had a problem in Z, namely to bound the number of solutions to a certain linear equation with the variables lying in a given set of integers. By using several other, a number of devices, but mainly number is large C, which is, as I mentioned, related to the restriction theorem for the primes, you are able to reduce it to a problem in Z mod U. So this is what one calls the local problem. Then by means of actually 2 applications of Holder's inequality, you finally reduce to a problem modulo prime numbers. And this is a problem that you solve. And with that, you get the required bound for the additive energy. So there's a progression from Z to Z mod UZ, where U is a square free number, to finally a question in prime numbers. This is the strategy for the primes, and this has remained the strategy for all the problems that we have considered. So for the squares, when you do this, the problem that you get at the end is this, a local problem in the squares. So let's take any integer t and k, an integer between 1 and t, and see a fixed element of finite field, in fact, prime 1, so fp for a given prime. And then look at these equations. So zij squared, these are variables, xi squared plus yj squared plus c, I going from 1 to k, j going from 1 to t. Now the number of solutions we can show is satisfies this bound for k between 1 and t by 2. Okay, and p large enough. I have not written the exact lower bound for p, but one can write it down. So for k between 1 and t over 2, we have this bound. And in principle, one would expect that this is true for k between 1 and t. So this variety that you have here, if you find the shape a little curious, it's simply because it results from 2 applications of Holder's inequality. So this zij's being related to xi squared and yj squared just come from Holder's inequality. So you, for the squares, you get this. For higher powers, you can write down a similar variety very easily. And this really controls the final part of the bound. Namely, you get a bound for sk, which is k times some fudge factor. And to get the optimal fudge factor, you have to get, at least by this method, an optimal count for the number of points on this variety. So for squares, we had a bound which is k exponential 3 log 2. If the correct count for the number of points on this could be obtained, you could just simply copy the rest of the method and you would get 2 log. Whether you get log 2 itself, I really do not know whether log 2 is the correct answer or not. Some on Mondays, Wednesdays, and Fridays, I think it's one thing. On Tuesdays and others, I think it's the other. So I just can't make up my mind if 2 log 2 or log 2 is the right answer. But I know that if I can get the right count for the number of points on this variety, I can at least get 3 log 2 to 2 log. So with this, let me stop. And sorry for technical issues.
Thank you very much, Surya. Thank you.
Have I exceeded the time much?
Yes, we have less than 5 minutes before the next lecture. So
sorry.
maybe, yeah, So you were speaking of monochromatic sums, but I see that you are very familiar with the colors when we look at your slides. So congratulations, and thank you for this beautiful talk and the lively talk with many colors, colorful talk. And so maybe we have time just for one question. Is there some question? No, okay, so it's better because we have now 4 minutes before the next talk. So thanks again, and
Thank
meet
you very
you
much.
in 5 minutes.
Okay,
Okay, thank you.
right. See you.
Хорошо.
Shall I share my screen?
Yes, go ahead, Srini.
Srini, today is March 18.
Hello, Srini. You are here? Nice to meet you. You could put your microphone.
Srini, you are muted.
Yes, but Srini should put his micro on.
He has muted himself. He has to
Okay.
unmute
So
himself.
now it should be okay.
Yeah, you can hear me now?
Yes.
Okay.
Okay, so now it should be okay.
So you are able to hear now, Michelle?
Yes, now it's good. Thank you.
Okay.
And we can see your slide. You share the screen.
Yeah, there is a typo pointed out by Shankar. So it should be March 18 rather than January 18.
Oh, yes. When I saw it was written, you are sharing your screen, I thought I was making a mistake, but no, it was your screen. So you're in Chennai now, Sini?
Yeah, I'm in Chennai. Yeah, we are not going anywhere. We are
Yes.
tied here.
But you're at home?
Yeah, I'm at home.
Okay. So are you ready to start now?
Yeah, I'm ready.
So can we start? Okay.
Sure.
So it is my pleasure to introduce the second talk of this session, which will be given by K. Srinivas, gaps between zeros of Epstein zeta functions. So please, Srini.
Yeah. Thank you, Michelle. And I thank the organizers for such a wonderful event. Unfortunately, it is online. It would have been much nicer to have physical meeting in Chennai. And so my talk is gaps between zeros of Epstein zeta function. So this is a problem that I have been working for quite some time on the zeros. And there are some interesting developments that I would like to share with all of you. So before that, so the plan is I will first briefly describe what is the Epstein zeta function and some results that we know and how we got improvement over that, and then the recent work that is going on. All right, so that's roughly the plan of the lecture. All right, so let Qxy be a positive and definite integral quadratic form, and Rqn, the number of solutions of this equation, Qxy is equal to n. Then associated to this Q, one defines the Epstein zeta function as zeta Qs is summation 1 by Q xy to the power s, and one can write it as Rqn by n to the power s in the form of Dirichlet series. All right. And the analytical properties of this function, zeta function, is well known. For example, zeta function, this Epstein zeta function can be analytically continued to the entire complex plane, except for a pole at s is equal to 1, which is simple, and residue 2 pi by square root of delta. And we will denote delta by 4ac minus b square, which is, since it is positive definite, so delta will be bigger than 0 with this symbol. And it satisfies a nice functional equation of the Riemann zeta type, gamma s going to 1 minus s with these factors. All right. And we shall assume that delta is not a square, so that square root of delta is irrational. Other cases like delta is 4 and all these things, trivial cases, are either easier or well known. Now, h of square root of minus delta, let it be the number of inequivalent forms with discriminant minus delta. Okay. So there is a way of defining equivalence among the forms. So let h delta denote the class number. Okay. It is well known that there is a one-to-one correspondence between the equivalence classes of quadratic forms of discriminant minus delta and the ideal classes of the imaginary quadratic field. In fact, the Dedekind zeta function and the Epstein zeta function, they are related in this way. Okay. So where L denotes the number of units in the field K. Okay. Now, the Dedekind zeta function has an Euler product, and therefore one can reasonably expect a Riemann hypothesis. However, if the class number of these quadratic forms is bigger than 1, so in this talk I will only talk about positive definite integral quadratic form. So when I say quadratic form, I mean this one. Okay? Then zeta QS has no Euler product. And the Riemann hypothesis fails to hold for it. Okay? In fact, Davenport and Hellgren in 36, they had shown that if the class number is bigger than 1, then it has infinitely many zeros to the right of line 1. So S will always be sigma plus IT. So sigma is the real part of S. And Voronin in 76, in fact, he showed that in the critical strip between half and 1, there are at least T zeros in a box of height T. Okay. Chawla and Selberg, they showed the existence of a real zero between half and 1. And Bateman and Grosswald, they improved it in this way, that if K is bigger than this, then there is a zero between half and 1. Stark, he proved that the existence of a number K, small k actually, this one, that if, if K is bigger than K, then all the zeros of this are simple. In this rectangle, they're simple with the exception of 2 real zeros between 0 and 1. He further gave a density, zero density estimate of this type. Okay. Therefore, though this Epstein zeta function has infinitely many zeros off the critical line, nevertheless, it has infinitely many zeros on the critical line, and that is our interest. Okay. So, in fact, the first result was by Porter and Titchmarsh in 1935, who showed that there is a zero half plus I gamma of this Epstein zeta function with gamma lying in T to T plus T to the power half plus epsilon. So we will call this as gap, this number, T to the power half, T to the power theta. Okay. So this was proved in 1935, and till 1995, this was the best known result. And Shankar Narayana, he managed to improve this result by removing this epsilon and replacing it with log. All right. And the next, so this was a barrier, like this half looked like a barrier, this exponent half. All right. So in 2005, Zutila and myself, we showed that, in fact, we can cross this half line to the left of half, and we managed to go up to 5/11. The moment we crossed half, we just left it there. Okay. And more recently, with Stephen Baer and Usha, we showed that, in fact, this 5/11 can be improved to 3/7. Okay. This is the recent result. This is for positive definite quadratic forms. And we are thinking about indefinite forms, but that seems to be very difficult. And in that case, still Shankar Narayan's result, this one, is the best one. Right. So in this talk, I would like to discuss how we got this improvement of how we crossed this half barrier, and then only talk a little bit about this recent development. That's the plan. So basic idea of the proof goes back to Hardy. Okay. In fact, all the proofs of showing infinitely many zeros for any well-behaving L function or a zeta function, most of the proofs, they depend on, the approach is by Hardy, which was simplified by Hardy and Littlewood, who showed that every interval of the type T to T plus H contains the ordinate of a zero of zeta half plus I gamma, with h e to the power 1 by 4. In fact, this is a very elegant proof, very nice proof by Hardy and Littlewood. And all the proofs that I know of theorems on gaps or theorems or Hardy analogs of Hardy's theorem for other L functions, they somehow imbibe this. The basic approach is this one. So this is amenable for generalization and all these things. All right. So what is the starting point of Hardy and Littlewood? The starting point is look at the functional equation and catch hold of this Hardy's function, WT. Okay. By functional equation, this f of half plus it is same of f of half minus it. Therefore, WT is real for real values of t. Okay. And also, if you take absolute value of WT, this is same as absolute value of half plus f of half plus I. Therefore, the zeros of that and the zeros of this will come from zeros of zeta q of half plus I. Okay? Because the gamma functions will not have zeros. And therefore, in order to show the critical zeros of this zeta function, it's enough if one can show that WT, this function, has real zeros, okay, for real values of t. So that is the basic point. And so therefore, assume that WT has no zeros in the interval t minus h to t plus h. Okay. With h, we will find what is h. Okay. This is the gap that we want to find. Okay. And take a smaller number, h naught, which is slightly smaller than h, and consider the integral I. This is on the half line. All right. So now, by our assumption that WT has no zeros in this interval, it follows that the mod of the integral as same as integral of the mod, because there is no change of sign. All right. And if this equality is violated, then it implies that there is some t in the interval t minus h to t plus h, for which the zeta function vanishes. That means there is a zero. There is an odd order zero. So this was the idea of Hardy and Littlewood. And so therefore, the entire thing is now how to show that the equality is violated. So if one can show, and then for what h one can show. Okay. So the contradiction is achieved by estimating the integral from above and below, provided h is 3/7. Okay. This is the recent Stefan and Usha's. Okay. All right. But we will describe about 5/11 first. So as it happens, in most of the problems, when you want to show, one of the step is easy and the other step is very difficult. Okay. So here also, one has to find an upper and lower bound for the integral I, mod I. Okay. So estimation from below, lower bound, is extremely easy, thanks to a general result of K. Ramchandra on the mean lower bounds, first power mean lower bounds for a general Dirichlet series, which says that there are points where, if under certain conditions, the function cannot be too small. Right? And okay, and this was simplified by R. Balasubramaniam, and it is written in a more usable way, because the original theorem is pretty long and too complicated, and it's very difficult to guess that, in fact, this is what is being said. So luckily, like Balu has managed to put it in a more human way, which has been very helpful for many mathematicians, because they can simply apply this one. So what it says, that you have a Dirichlet series, Bn by n to the power s. Not all coefficients are 0. And suppose it has analytic continuation up to some number a, to the right of a, and there it has a polynomial growth. Then it says that for every epsilon, this is at least h. The integral is at least h. Okay, and the main point is h can be as small as log t, a power of log t to the power epsilon. Okay, so for in showing the upper and lower bounds for the integral I, the lower bound is very easy. And as you can see that it is a very general, for you take any general Dirichlet series, for example, a series which belongs to Selbert class, we know that it has a polynomial group, and you can apply it, and you can find the lower bound as bigger than h, for any h bigger than a power of log t. However, it is the upper bound which is the difficult part, most difficult part. And as you saw before, Hardy and Littlewood, they could manage that the h is only about t to the power 1/4 plus epsilon. Of course, that was improved by, for zeta function, that was improved by Balsubramaniam to t to the power 1/6 plus epsilon, and Karatsuba to 5/12 plus epsilon, and so on and so forth. Okay. Yeah. So the hard part is finding an upper bound for the integral I. All right. So we start with this I. I is this integral, and then you see this zeta function, half plus I t plus u. So there are two ways here. Either one moves the line of integration from half to 1 plus epsilon, like how Hardy and Littlewood they did it to get t to the power 1/4, and all other methods also. And Shankar Narayanan, he moved it to one line, and he could remove the log t part there. So either one can move the line of integration to the right, or one can stay on the line half and use some approximation to this zeta function. Okay. So therefore, this needs approximate functional equations, and here is the approximate formula for zeta half plus it, which was developed by Jutila for cusp-form L functions, and the same proof follows for our Epstein zeta function also. Okay. So here, look at the form of this one. Zeta half plus it is for any x, it's up to x plus x to 2x, this thing, plus these are the errors. Now, if you take x to be t to the power cube, you see that this is t to the power 3/2 by t square. So, and this is also, so both of them are of the order t to the power minus half plus epsilon. So these are the errors. Okay. Therefore, one substitutes this approximate formula into this integral that we have here, and then this takes this form, and this is the error. So here, the main thing is, in all of this business, there is a particular sum which gives problem, which becomes too big. Okay. And that in this case, the sum is around when t, small t is around t by 2 pi, with square root of delta. Okay. If you look at a Selbert class of functions, then one needs to do this kind of things for sums when n is close to t to the power d by 2. All right, a certain sum of this form. And if you can show that this particular sum is small, then you can get a good gap theorem. So here we extract this sum, this critical sum, and this k. What is this k? K and h are related by this thing that k times h should be around t. This is the relation, okay, between k. So you want to show a gap of h, then you need to look at a gap, estimate this one around capital T in an interval of length k, capital K. Okay. So the object is to show that this exponential sum is small. Okay. And the other terms, apart from this, all other terms can be shown to be very small. They don't contribute anything. They go to error because of Stirling's formula for gamma functions and all. Okay, and also complex integration. All right. So yeah. Therefore, our crucial sum, our integral I is this one, this one plus this one, second one, and crucial sum appears here in the blue color. All right. Now, rest of the things can be shown to be very small. Only thing one needs to consider is the one in the blue color. Okay. So therefore, the estimation of the sum S2. Okay. This is the S2. And so, yeah, rewrite that one in terms of this one. And then finally, we have t minus h to t plus h, gamma of half plus it. RQ, this is the smoothing factor. This is 1 whenever n is around t by 2 pi at an interval of length k. Okay, so this is the sum we are looking at. Okay, and hence our S2 is h times supremum of t minus small t less than or equal to h, upper bound for this exponential sum. Okay, this Dirichlet polynomial. Okay, therefore we need to choose the parameter k as large as possible so that h can be made as small as we want. So the objective is to show that this sum is less than some t to the power minus epsilon, okay, whenever t and t are at a distance of h. Okay. Then combining with the previous estimates, finally one can obtain h is equal to upper bound to be less than h naught times log t to the power minus 2. And remember, by using Ramchandra's theorem, we have a lower bound bigger than h naught. So that leads to a contradiction. Okay. That is the basic idea of the proof. And therefore, how to estimate this crucial sum? This sum I will keep calling as crucial sum or the sum in question. Okay, we would like to discuss how to transform, how to estimate this so that we can make it small. Okay. So this sum is first transformed into another sum by using Voronoi formula. And that Voronoi summation formula is then transformed into another by using saddle point method. Okay. So this is the basic thing. And the Voronoi formula in question involves an additive character related to a rational number. And a rational number, suitable rational number is chosen among the convergence of the continued fractions of the quadratic irrational 1 by square root of delta. And this is because quadratic irrational the continued fraction is periodic, which allows to control the denominators of the partial quotients, because the partial quotients are bounded. All right. So I would like to explain a little bit about the summation and the transformation formulas that we have. So note that whenever we want to estimate sums of the form Bn, Gn, and e to the power 2 pi I Fn, where Bn's are arithmetical functions, Gn's are complex valued, and Fn's are real valued in some interval. Okay. So if f dash of x is close to a rational number, h over k, this sum in 12 and sum in 14 are of the comparable. Okay, they're of the same size. The difference is very small. Okay. Therefore, this sum can be replaced, 13 can be replaced with 14. Now, if a summation formula for this sum 15 is known, then we can sum 13 by partial summation by parts. Okay. Partial summation. Okay. This is a standard thing. So in our case, we have our Bn's as Rqn, Gn as n to the power minus half, Fn as minus t by 2 pi log n, and therefore we look at the sum Rqn n to the power minus half, e to the power minus t by 2 pi, e to the power 2 pi I times this one, okay, minus t by 2 pi log. Okay. So this is what I was saying, that once we have a sum for this one, then one can sum this one by partial summation by parts. All right. And Utila has obtained this Voronoi summation formula for RQN with the additive character EKN by H. Okay. And so this is of this form. So here's, so this Voronoi summation formulas are available for when these coefficients are Cusp-Formal functions and quadratic forms, and I think mass forms by Moidman, I suppose, and very few other things. So one invokes this sum formula into this summation. All right. So one gets, so this is the summation formula. Now this is the starting point. Once we have a summation formula, okay, so then we get, in our case, we get RQN, EK, NF, FN to be of this form, okay, where J naught is a Bessel function. Okay. So this summation formula serves as a starting point for the derivation of a transformation formula for exponential sums. So the exponential sums in questions are transformed now by using this summation formula. So which means, okay. Now, instead of applying directly this sum S, it is advisable to use a smoothing version of this. Okay. Namely, 1 by u, 0 to u, SU t, where SU is this. Okay. Now, the difference between S and S prime is not big, so they're small. Now you can write SU as this sum by removing a factor MR and then multiplying e to the power MR. This has a lot of advantages. also use van der Korput's estimate in the X variable. And this allowed us, this showed that, so therefore, in order to show that crucial sum is O of t to the power minus epsilon, it was enough for us now to take k is to be t to the power 4/7 minus epsilon. And therefore, we could obtain the gap to be t to the power 3/7 plus epsilon. So this is the recent result. And these are the things that we have used. This is a Weyl differencing. So this rearranges the sum in a more amenable way. And then the B process, we have used the B process. So the Weyl shift, it affects the, it reduces the original sum to a more tamely oscillating one. Of course, at the cost of loss of some accuracy, but we have managed to do that. And then the van der Korput's lemma. This is the one we have used in the other parameter. So then the final estimate comes out to be, this was there before, and then we managed to save something more. And finally, we got k to the power 7/8 by t to the power half log t plus t to the power k to the power 17 by 8 and t to the power 3 by 2, which is O of t to the power minus epsilon, provided k is about t to the power 4/7. So k is t to the power 4/7 means h is t to the power 3/7, because h times k is about t. All right. And now the other details are very technical, so I don't want to discuss. I didn't want to discuss those things. This is there in our paper in functional approximatio. Okay. And all the details are there in the both papers and the references of this paper, where Jutila's development of exponential sums related to quadratic forms is there. And since this is the last day of the talk and such a long conference, people must be tired also. I didn't want to make too technical and giving too technical details. So I would like to stop it here by thanking all of you. And I wish Balu a happy birthday. He has been extremely helpful in my career. And I wish him a long and healthy life. Thank you very much. I stop it here.
Thank you very much, Srini. Very interesting. You see, in my experience, when we have an integral, most often what is difficult is to give a lower bound, and what is easier is to give an upper bound. But I see that here, thanks to this lemma of Ramachandra, it is quite the opposite.
Yes, indeed. So that's a very beautiful theorem.
Do you expect that the lemma of Ramachandra is optimal?
Sorry?
Do you expect that this lemma of Ramachandra is best possible?
I mean, this is best possible is I don't know, but this is the best one can expect, because
yes.
This, I mean, we would like to show that there are infinitely many points where the function cannot take small values. All right.
Yeah.
So
yes.
There is a well-spaced points between t to t plus h where the function is large, and that's enough. Because on the other hand, uniformly we have shown that the function, the values taken by the function are small. So that leads to contradiction.
Okay, thank you very much. Are there some questions from the participants?
Yeah.
Professor
question.
Yeah. Professor Walshmate.
Yes.
I mean, suppose you are to the right of 1 for theta function. This is definitely best possible. Even to the right of half, probably you can save a log t power 1/4. But to the left of half, for example, for theta function, this can be definitely improved.
Okay.
Nice.
Okay. Thank you for the comment. Thank you, Balu. And so, any further comment or question?
Stefan.
Yeah.
Yes.
So thank you very much for the nice talk.
Yeah,
So I remember we wanted to look at the indefinite case too.
You're right.
Maybe
right.
you can say something about difficulties.
Yeah.
That come
So
up in that
the
case.
problem is, as I said, for the indefinite case, it was the Hardy's theorem was proved by K. Chandrasekharan and Raghavan Narasimhan. Okay, and then their proof also gives half plus epsilon, and the epsilon was removed by Shankar Narayana. So Shankar Narayan's result is still the best known for the positive definite. In our case, we were looking at Voronoi summation formula, and also the problem becomes, because now this RQNs, the bound, the summation for RQNs, they give trouble because of existence of units and things like that. So we need to, because now the curve is unbounded. So we have to restrict it into certain, regions and then do it. So there is a possibility of doing it, which we will explore. So there is a hope that we will be able to do it.
Yes.
Yeah. And Jutila also expressed positive hope that it can be done.
Yeah, let's look at it.
We shall. So let formula subside a little bit.
Mm-hmm. Okay, thank you very much.
Thank you.
Okay, thank you.
Sir.
Any further question or comment?
Yes, I have a question. So, sir, if you consider any NRE positive definite quadratic form and consider corresponding F10 zeta function, so where is the actual difficulty arise if you going through your method?
Yeah.
You
The difficulty. See, as I said, the difficulty when you represent it as an integral, you see that you have the e to the power 2 pi I times f of the function of n and t. All right.
Yes.
In the integral. Now, when you take the derivative, the saddle point, catch hold of the saddle point. The problem comes precisely around the saddle point. All right. So if you are able to show that the sum is small in a neighborhood of the saddle point, then you are done. So here, as I said, t to the power in a degree d case, you have to estimate the sum closer to t to the power d by 2 in a small interval of length of around t to the power d by 2. Other things you can do quite easily by the method that I described.
So this lemma by Jutila, this is also true for general case also?
Wherever you have Voronoi summation formula, you can use this.
Okay. Okay, thank you.
And we have a result for Selberg class up to degree less than 4 under certain assumptions. You can look at Krishna Rajan's thesis. There's a chapter in that. So that will give you where is the trouble, where is the actual crucial sum that comes.
Okay.
Exactly. This Hardy and Littlewood's idea.
Okay, thank you.
So thank you for this answer, Srini. Any further comment or question?
Yeah, I have a question, if I may
Yes,
ask.
please.
So can you consider same thing for, from your method for the linear combination of this function? Because in the beginning, as you mentioned, the Dedekind zeta function can be expressed as linear combination of function.
You can also look at the linear combination. As I said, for it is possible, provided you have functional equation. Of course, you have. I mean, if all the functions have the same functional equation, then you have a linear combination. You can do it for linear combination.
So are you saying that doing for the linear combination will give same estimate for Dedekind zeta functions? I mean, from in one slide.
See, for Dedekind zeta function, or you are talking about comparing Dedekind zeta function and the partial zeta function.
Yeah, so there was a slide in the beginning, right, where you expressed Dedekind zeta. I mean, sums of abstract zeta function. So I'm wondering that if basically having estimate for the linear combinations, so can we obtain the similar result for Dedekind zeta functions?
Yeah, I mean, you are showing the, I mean, you are, see, this method will give you the zeros of each of this partial zeta functions, right? And therefore, combining them, you can say that the Dedekind zeta function also. For example, if the class number is 1, let's say, then the Dedekind zeta function is the Riemann zeta function times a L function of a quadratic character. In this case, trivially it follows. But if you have a linear combination, then also it will give you information. Balu, I think I'm saying correctly, right?
Yeah, I think it should I mean follow. Although like showing the sign change of the linear combination, sometimes it's a little bit more tricky. As you know, the Selvar conjecture for V12 function for linear combination, it's like.
In fact, Bombier and Hazal, they have looked at linear combination of L functions which satisfy a certain type of functional equation, and they talked about the zeros of this linear combination.
Sudhir, suppose you start with a linear combination, how do you construct a real function out of it?
That's why there's some conditions. Some conditions are required so that they should have.
The whole harness method is first of all by getting a certain real function.
Yeah, so there are, I think, 2 ways in our recent paper with Mithun. So one criteria we have given even for complex linear combination under certain restrictions. And the other way is you look at the individual Hardy G function, all of them are real, and you look at their sum.
Okay, I see.
Yeah, but under some conditions. Other way also where we have given in a recent paper with Mithun Kumar Das, a complex linear combination also we have generalized how to make it real under certain restrictions.
Yeah, then it should work.
Yeah. In fact, in our paper also you have seen, Sudhir.
Maybe in the linear combination, if you have some common Euler factor, then possibly Karatsuba has some result.
No, Euler factors you will not have, you see.
No,
I mean,
some common factor. Some common factor.
But if they satisfy the same type of functional equation, then it is possible that the linear combination, you can write the zeta function, Hardy's zeta function. It is there in Bombier and Hazal state.
If the gamma functions are the same, then of course you will get a same functional equation for everything, right? So then there's no problem.
Right.
But that's a pretty rare event and certainly not going to happen in your case, I think.
Yeah, we look at individual L functions.
So thank you very much. There was a very interesting discussion. So it was very good, Srini, that you left enough time for this discussion. And so I thank you again. And I close this second talk. And then we meet in 7 minutes for the third talk of this morning. Thank you very much.
Thank you. Bye.
Hi, Sinu, are you there? Sinu?
No, he didn't join yet.
I'm trying to contact him. I will get back.
No, I called him some 10 minutes back and he said he'd be coming.
Hello? Yeah, I can't hear anything from the. You can see me. Can you hear anything from the mic? Because it seems.
Yeah, we can hear you as well.
Okay, excellent, excellent.
Yeah.
Okay, great. Sorry.
There's still 2 minutes remaining. The chair will introduce you.
It was put mute.
Yeah, you can share maybe.
Yeah,
Sinu.
yeah, start that.
Hi, Sinu.
Yeah. Yeah. Can you hear me?
Yes, perfect.
Okay. I will share.
So I see that your name is Sciences UFR Math Licence, but you are in India.
Yeah. In fact, yeah, this is the Zoom account that I was using for my classes in Paris, because it was an account with, which allows that to have more than 50 participants and so on. And but now it's registered in my Zoom, and I don't know how to use a private one. So when each time I launch Zoom, it logs in this account. So that's
Okay, so I think it is time right now. So do we start?
Yeah, when you hit right. Yeah.
Okay, so I am pleased to introduce the third speaker of this session, Sinu David, who will speak on special values of polylogarithm, PADE, irrationality, and it is a joint work with Makoto Kawashima and Noriko Hirata Kono. So please, Sinu.
Okay, thank you very much, Michel. Thank you very much, everybody. It's a great pleasure for me to be talking at this lecture with honors of Balu's 17th birthday. Happy birthday, Balu. And it's a pity because we cannot have this be all together in IMSC for this meeting. It will be for the 75th birthday. So today I want to talk about irrationality. So let us start with standard things, very, very standard, to see how which methods we should know, and then we'll introduce our results. So the first way to prove, probably the oldest, to prove the irrationality of a number is to have an exact computation. So the classical example, going back to antiquity, is the irrationality of square root of 2. You have a formula, and then you perform some basic number theory, and you deduce that the number square root of 2 cannot be rational. Of course, this cannot work very often. You need to be lucky enough to be able to perform such a thing. And but finally, a very modern way. It's so you see, the time has shrunk. It's less than 200 years ago. Liouville philosophy use approximation. So you have a real number. You just assume that you have a sequence of numbers of integers, Pn and Qn. Qn will be the denominator, and Pn is the numerator. So we assume that alpha n, alpha, so it should be alpha, sorry, I have made a misprint there. You assume that alpha is getting closer and closer to the fraction Pn over Qn. And then if you assume that you have such a thing, it goes to 0, but the number is not 0, that's the crucial part, then alpha is irrational. So you have to be able to achieve closeness and non-vanishing. So of course, as soon as you have made this remark, you want to understand how close irrational number can become closer to rational. So how, what is the best possible approximation? And you have an easy definition. So you introduce just the following equation: alpha minus a over b less than 1 over b to some power, whatever the number, so just r. And you want to know whether such an inequation has infinitely many solutions or not. And the measure is the largest value for which you still have infinitely many solutions. This is a measure of irrationality. So what do you know about the measure? Of course, if alpha is a rational number, 1 works fine, because you can write infinitely many ways with an exponent 1. If alpha is irrational but algebraic, then the measure is bigger than 2. So you can use continuous fractions to prove that. And the golden ratio is, of course, the worst possible approximation. And so more involved, you can show that you have infinitely many numbers with irrational measure which is equal to infinity, which are really badly approximated. really very well approximated, sorry. And these are Liouville numbers. But they are transcendental. And then, of course, Roth's theorem tells you that every algebraic number, which is not rational, has a measure of 2. Okay, this is more involved than the first results. So irrationality sequences and measures, you need to find the correct exponent. Okay. Now we want to have something better. We want to have several numbers. So you have given several real numbers, and you want to know whether they are linearly independent of a Q, whether the space they span is larger and larger. So recall that Michel yesterday talked to us about transcendence. The transcendence is linear independence of monomials. So this is the first case. So you want just to have linear independence of monomials of degree 1. And algebraic independence is far more complicated. So we concentrate on linear. So if we want to have, we need a proper way of generalizing this relation of Liouville, the first one that I show you. Just can we formulate an easy way, workable way of saying that this is true? Okay. So you take Michel Laurent has a nice result. Maybe it was known before, I don't know, but it's a nice way of saying things. So you just take a bunch of real numbers, R1, Rn, and you assume that you have, so you want to say that the numbers are 1 and these real numbers are linearly independent of a Q, and this is equivalent to the fact that you have a sequence of linearly independent integers for which all the numbers are well approximated, better than the denominator of the fraction. So you see, you have a fraction numerator divided by Qi, and you want the approximation to be better than Qi. Okay, and as soon as you have that, you can ensure linear independence. So this is a fairly easy way of saying that. And of course, the non-vanishing hypothesis that you had in Liouville translate into the fact that these need to be linearly independent. Okay, now, so the thing that you want to do is to have special numbers which are given by arithmetic functions, and you want to try to show that they are irrational. You expect, of course, most of them to be irrational, but it's very difficult to prove in most cases. So we are going to introduce what is our choice of theta that is going to be of interest to our study today. So we are going to work with polylogarithm function and large functions, which are slight deformations of this. So I look at the polylogarithm function. This is the following Taylor series expansion. So zk over k to the s, essentially. And now you want to have, you just fix a number field, you take some algebraic numbers, and you say, okay, can you expect all these polylogs of alpha i's to be linearly independent over Q? Okay. So very natural question, because these functions are so transcendental that you don't expect them to have to take rational values. But still, of course, it can be wrong. And you have an obvious relation. So you just take log 4, because if s is equal to 1, you have just the standard log function. Log 4 is equal to 2 times log 2. So obviously, you can have two numbers. 4 and 2 are algebraic numbers, rational numbers, and you can have a relation. So you need to kill these relations. And so what we are going to do, this is very classical also, is to take a metric condition. We are going to ask that all the numbers we are taking are close to 1. And then essentially this will not allow algebraic relations of this kind. So this has a long history. In the 70s, the Russian school, Nikisin, for example, proved the linear that if you take just one rational number, then this LE is irrational. So each taken individually are irrational numbers. So this is for rational numbers. The field is Q. Okay. Atta is proven also for the D log. Very sharp. As soon as 1 over Q, so you see close to 0. As soon as Q is bigger than 7, so pretty small number. And Rhin Viola, and I've improved that. And then you have something that is closer to what we want to do, is done by Viola and Zudinin pretty recently. So you take several numbers, exactly as I said. You take several polylogs because you have the standard log and you have the D log. And you take different algebraic numbers. So you have 1 over Q 2 times and 1 over 1 minus Q. So essentially two different alpha i's. And then you have linear independence. Okay. And Rhin-Taufin have a general thing, but for logs. So you assume now that alpha i's are imaginary quadratic numbers, so either rational or in Q of I, say, or Q of I root D. You assume that you have a proper metric condition. All these metric conditions will be very similar and will translate to, if you have just one number with denominator bigger than 7, 10, or 2000 or whatever you need. And then all these standard logs are linearly independent. Of course, this is not new because Baker theorem tells you that you have something like that. But the point is that when the metric condition holds and when the Rhin-Taufin theorem holds, the bounds are even better than Baker. So very specific, but they are even better than Baker. And even more important is the approach that they have used, which is proving to be very fruitful. So our work has been pretty inspired by the reflections of Rhin and Taufin. And then I can cite some other more global results. So you go to the G functions. So you take a bunch of G functions. You assume that they are independent as functions, so over the field of fractions of C. And then you assume further that this is satisfy a system of linear differential equation. So this is important. Then the numbers, the special values are linearly independent, subject to a metric condition, and still subject to the fact that your algebraic number field is contained is an imaginary quadratic. So there is a strong restriction on the field. All these approaches worked for the fields to be equal to Q or imaginary quadratic numbers. So this is a restriction that we want to address. Okay. So now what is Lodge function? You just take a real number and you shift the denominators of the exponential series. So that amounts to taking a shift in the differential linear differential equation satisfied by the D log or the polylog. So you had for the polylog you had just x is equal to 0, so the denominator is k plus 1 to the s. Here you have some small x, which is like k. And these functions satisfy the same properties, and you can ask whether these numbers are linearly independent, letting x vary, alpha vary, and s vary. Okay. So for the time being, for this lecture, we shall assume that x is rational number, firstly, so not an irrational, and secondly, that x is fixed. So you can think, if its notations become too complicated, you can think of x is equal to 0 and you just have polylogs. But for the time being, we assume that x is fixed. And at the end of the lecture, I'll try to address the last part. Okay, so now what is our result? So you take some x, as I said, a rational number. You take some number field, and you fix a place. It can be either a p-adic place or an Archimedean place. You don't mind. You take numbers. You assume that these numbers are pairwise distinct, and you consider the bunch of special values of the polylogs of the Lodge functions that are associated to that. So you think that beta is a large integer. So you are going close to 0 because you divide by beta. Okay, so it's written like that because of this philosophy, because we want to have beta different. So you have the metric condition. I have written it here. So you need the absolute value of beta to be much larger than the height of the point alpha beta. Okay, so typically 1 over q works because alpha is equal to 1 and beta is equal to q. So the height, the absolute value is much bigger here than at the other places.
Sinu, may I ask you? You fix the place of k, but the numbers that you consider, they are complex numbers, or they are in the completion with respect to V0?
They are in k, and each of these series converge for this place. Okay.
So these numbers are in the completion of
k in the
completion.
So this equation is written for the usual complex numbers, but you can write the same thing for periodic completions.
Okay, thank you.
So the same series actually converges at any place. Okay. So where I am. This print here. So the metric condition tells us that the denominator needs to be large enough compared to the numerator. So I see I have a misprint there because I should have put Rm plus 1 here. Excuse me, because otherwise this would be always negative because you have the height of beta against absolute value of beta. So I forgotten a Rm plus 1 at this place. It has been corrected here. So for this to be true, the height should be really concentrated at the place V0 that you are considering, right? And otherwise it cannot work. Okay. So typically the case 1 over q, like considered by Han, Tufan, and others. And once alpha I is possible, you fix the alpha i's, and you can, provided that you take beta to be a large enough integer, at some point of time this will become true. Okay, because as soon as you increase this, again, think that I forgot this Rm plus 1 here. This number, if you take just a rational integer, and this is the standard Archimedean absolute value, this will become larger because you have a plus 1 here. At some point of time, it will beat the other. Okay. So the condition actually is true for any big enough beta. Okay, and there is something that I would like to mention is that we have this time we have no restriction on the number field. So this is the main difference with the previous results, where the field was restricted to be a quadratic imaginary number field. And yeah, there is maybe one question, naive question that you might ask is that this